So microservices, it's this wonderful new buzzword that's been tossed around a fair bit lately. I've seen a fair number of people approach the word and try to define it with a certain amount of strictness in saying, oh, a microservice can be only a small team working on the service. You can have no more than X number of people. They can't be working on anything else at the company. The service is their entire, life's work. I'm really not of the opinion that that's a terribly useful definition. I think it's actually really a means for them to be able to point at things and saying, yeah, you're not doing it right. Overall, not that helpful, but somewhat more helpful are the comparisons I've seen of microservices versus service-oriented architecture. SOA is broader in scope. Microservices as a term seems to be a lot more focused. It's something that's arisen lately. It's arisen out of the internet industry, of which I'm fairly comfortably a part. And I think it reflects a certain amount of best practices and experience, and is kind of evidence of maturation in the field itself. But at the end of the day, it is also a red herring because microservices really are a kind of service-oriented architecture. Though some would say that it's SOA done right, and maybe in the internet industry, but I've also worked for a really large hospital, and service-oriented architecture there in the old school sense with Java Enterprise Service Buses and all the rest of fun stuff like that has a valid place there. Let's talk for a moment about the pluses and minuses, the pros and cons. Microservices are contrasted very frequently with monolithic applications. And I think one of the big wins over monolithic apps is that with a monolith, you tend to accumulate complexity within the code because you really need discipline to keep the components separate. It's a natural thing. You've got everything all in one big application. Of course, the components are going to talk to each other. The problem with that comes that the components start becoming dependent on each other, which means that the first time you need to change a component halfway down the stack, you wind up seeing rippling changes affecting every other component throughout the stack. Not that that's insurmountable. It is perfectly possible to build a nice, resilient, monolithic app. But microservices have a separation built in that makes it easier to stay simple and focused within a given service. And that means that, well, anytime you're looking at a given service, it's easier to know how to handle it, how to work with it. The cons, of course, are you're moving complexity from one place to another. Instead of having all your complexity in one place that's running on one big computer or maybe a big farm of computers, you have individual services running on separate computers. You've moved them apart, which means you now have to worry about making sure that they can actually talk to each other with some semblance of sanity. And of course, network partitions that, of course, according to Michael Stonebreaker, never happen, do happen on a very frequent basis, particularly if you're based in one of the public cloud infrastructures, such as Amazon's AWS. Which means you have to invest heavily in monitoring. You have to make sure that your system as a whole is structured in a way that it can handle errors gracefully. And that latency really isn't an issue, which means you have to start thinking in terms of, okay, I have a system, I have a service here, it's going to produce results. They may not be current when the user actually hits the website and asks for those results. They may be a bit delayed. And that's okay. It's just a matter of how you structure your application and how you set up the expectations of your customers. So how do we implement a Bitly service? We use Tornado asynchronously. Okay, no, right. That's the airplane. We use Tornado asynchronously. You know what? That's not a really positive picture either, so we'll just skip that part. Let's talk a little bit about conventions, because conventions are what keep you sane in implementing lots and lots of services. The very first convention that makes our life easier is a common response format for all of our services. They all look exactly the darn same. The status code, the status text, and then the data is embedded in a dictionary in this JSON response. This way, all of our APIs emit responses like that. It's very easy for us to figure out how to interpret results coming from one of the other services. We also have a common directory layout that we like to use. Again, we're implementing Tornado services. We're doing asynchronous Tornado. It starts to get fairly easy after a while to know where to look for stuff if everything follows the same format. We have a top-level service directory which contains our executables. The app directory implements the actual route request handlers. Conf scripts tests are obvious. Lib directory is going to be reasonably straightforward. It's going to be where we put our reusable code. It's also where we put just general library code that belongs specifically to this application. So at the top level, again, executables live here, and so do readmes. Readmes are a wonderful thing. Do more of them. Settings.py is something that you'll see in everywhere. It's basically a dictionary or a bunch of dictionaries. In our case, we do some interesting things when we turn these dictionaries into actual settings, where we distinguish which dictionary is in effect based on the environment. So we have our dev environment, which is living in a VM on our laptops and is running 50 billion services all at once. Actually, 50. And then we have, for instance, our Delaware data center or EC2 or any other environment that we happen to set up. And that separation works out pretty well for us. The other interesting bit that we have in here that I'm not showing you is we have a means of encrypting sensitive things like AWS keys or API keys for any given service. And that way we can keep those keys in our repository without actually exposing them as a security leak. It's a very handy little thing. One I highly recommend. So Service API is going to be the Tornado application itself. It's the executable that runs Tornado. And it's going to look a bit like this. We use a somewhat older version of Tornado. Well, we use a mix. Both of them are older, but one is older than the other. Tornado 1.2.1 and Tornado 3. Tornado 4 came out very, very recently. It's got some nice improvements to it. But yeah, so our Tornado application is going to do our basic imports. We're going to have our Tornado imports. We're going to have our request handler imported from app.api. We're going to set up an application. We're going to do a little bit of extra configuration there. We're going to do our URL routing. Yes, this is one of our services. This is why it is a microservice. There are only 5 routes that it handles. That's kind of the point. It's that simple, and that makes it easy to maintain. And then we have the part that makes it executable. If name is main, what port to listen on, check the command line for anything optional that might get passed through, instantiate the application, and turn it on. Start up the I/O loop, the event loop that actually listens for incoming requests. It's as simple as that. And that's, again, kind of the point, is that we're moving the complexity away from the actual service itself. We also have in here QReader implementation. QReaders are the streaming part of our streaming asynchronous web-based microservice architecture. And I'll be getting into that in greater detail a bit later, but I will show you the code now just for funsies. So we're importing Reader, and we're also importing our own little thing that talks to StatsD. StatsD is a statistics collection daemon for Graphite. One of the key things about running something like this is that you have to monitor it extensively, which means you have to collect metrics on everything. So that's what we're doing here. This particular QReader is pretty darn simple, and it's basically going to count stuff and shove it into Graphite. So QReader is something you use with a message queue. So you need to figure out whether the message is of interest. The message comes in, and if it's of interest, you return true. Otherwise, not. If it returns true, then it gets passed along to a message handler function. And in this case, like I said, it's very, very basic, very simple. All it's doing is looking in the message, and if there are spammy bits in the message, it's going to increment some stats_d counters, just saying, hey, we saw some more spam. The other fun part is this line at the bottom, which tells our queue implementation, NSQ, new simple queue. Yes, there is an older simple queue. It basically acts the message and says, okay, we're done here. You can throw this one away. We're done. You don't have to retry. Then there's, again, the executable section of this. If name is main, let's build a reader. Some of the interesting bits in here, validate message is the function you just saw a couple slides back, and we set that up as the validate method. Count spam actions, there's your message handler, very straightforward. Then there are some settings in terms of how to talk to NSQ itself. That's one of the parts I'll go into more detail on in a little bit. Service app is where we implement the Tornado request handlers. Basic is our base class, base handler. Notice def API response here. That is how we make sure that we're returning that common response format. Makes life very simple. So, yeah, this is a bit of a Tornado-ism. Self.finish tells Tornado to finish writing out the entire HTTP response and close the socket. It's the part that finishes off the async-ness of a given request. Makes life easy. But you have to remember to call it, because if you don't, it leaves the socket open, never sends the response, and you are hosed, which is all sorts of fun. So API, this is where you actually implement the handlers. Dead simple, normal stuff, right? Anybody who's done any web programming, this should look ridiculously obvious. We define a method that implements the HTTP verb get. We push, put, delete, post, whatever your standard HTTP verbs are, define a method, that's what gets called. Now, like I said, this is an older version of Tornado that we're dealing with, so there are some niceties that the newer versions offer. I will show you what a modern version actually does look like, but in this case, the method does some work, and down at the bottom, we've got self.getAllUnits, and we're defining a callback. If any of you have done any Node programming or twisted programming, yes, all of this predates Node by, heaven knows how many years, but a lot. Yeah, so we're defining a callback which calls this particular method when getAllUnits actually is done enough and returns enough results for Tornado to realize it and say, oh, okay, hi, let's do some more work now. So this decorator here is what makes it asynchronous. And necessitates the callback that you'll see defined here. You finish off the list. You're receiving data as a response. If there is none, toss an error. Otherwise, do some stuff. And then finally, send an API response with the output. And that is our common response format. The modern version of that is shorter and simpler and a little bit easier to think about. You don't have to think about callbacks specifically. Instead, you pop a gen coroutine on the top instead of the Tornado web asynchronous. And instead of callbacks, you yield from self-getAllUnits. Again, simpler, a little easier to work with. lib. Datastore interfaces, we use all the data stores, like all the data stores. MySQL, Mongo, React, Redis, Amazon Redshift, you name it, we have them. So your data store interface, in our case, is going to be very application specific or very data store specific, but this could just as easily be SQL Alchemy ORM. Speaking of which, Mike Bayer is giving a tutorial on that tomorrow. If you have a need to learn about it, that would be the place. He is the author of SQL Alchemy, and he's quite a pistol. He gives an awesome talk. So, Conf. Service Conf. Nagios. Hey, monitoring, right? Nagios. Nagios is where we do all of our monitoring. Nginx fronts all of our web services on each of our servers. So we wind up needing to do some configuration there. And then whatever cron tabs or any other conf that's necessary to get things running on a given server for a given microservice. Scripts, backup, restore, load. And RPEs, custom monitoring scripts for Nagios, they would all go here. That's really all there is to implementing a microservices at Bitly. It's easy. It's simple. That's kind of the point. But it's when they start working together that things get a little more complicated. Where does one cat end and the other begin? In our case, we have V3 API sitting in front, and it is not a microservice in the least. We have microservices in back of it that provide lower level raw functionality. V3 API, on the other hand, provides the public facing API. So we make a nice, friendly, easy to use URL with nice, pretty named URL parameters. We expose that to the public. That's where we do our authentication, authorization, our input validation and cleaning, and then we translate incoming requests from this nice friendly version to whatever the backend needs to actually speak something technical. So this layer is, you could kind of call it aspect-oriented programming, cross-cutting concerns. It does all of that for all of the actual real working stuff in the back. And it's large. But it's still conceptually fairly simple. In V3 API, you're going to have a file, a module for each of the individual backend services that knows how to call the backend service and does that. And we get pretty good performance out of this. So the other half of our success story is NSQ. Now, NSQ itself is written in Go. Go is our secondary language. Python is our primary language. We use Go because it's more efficient on the CPU and because Go routines are a wonderful thing. They allow us to do concurrency in ways that the GIL does not, which can become important for some of the stuff we're doing. So to trace the evolution on this, this is a basic web app. The web app layer is going to be Django. The database is going to be something like Postgres, or you could have Flask and Postgres, or Tornado and Postgres, or Bottle and Postgres. Okay, maybe my fanboy side is showing a little too much there, but that's okay. At some point, hopefully, your web app will get to the point where it has too many customers for you to service. So you're going to scale it out horizontally. That's your first bottleneck right there, is the web layer. Now, once you do that, you're going to eliminate the first bottleneck, your web layer. That means that you're going to expose the second bottleneck, which is your database. So at that point, okay, we add a caching layer. And yeah, so you have cache, and that caches some of the requests to your database and makes life easier for a little while. Eventually, though, you realize it doesn't help all that much because you've just got too much to do. So you replicate. And that works for a while, but then eventually you get to the point where you need to shard. And at this point, hopefully you've got enough scale to be good for quite a long while. But you're faced with a different problem. You're probably faced with it much earlier than this, and this is not exactly non-contemporaneous. Yeah, that's a good word. Yeah, I'll have to write that one down. But the problem that you run into with this is that the things you're doing I mean, you can service lots and lots of requests all at once, but each request still takes a really, really long time to finish because you're doing something absolutely silly like fetching Gravatar images and resizing them, or doing text analysis, or, again, stuff that just simply takes too long and makes your users pack up and leave. So the solution to that is to add a message queue and a worker, or workers. We should imply at this point that the web app box and the database box and the worker box can scale horizontally. In Python, the normal go-to for this is going to be Celery, right? So your backend queue is likely to be RabbitMQ or Redis. Those are the two production-worthy, and they're folks doing things with Mongo, but they're on their own. Enough said. The way that's going to work, the web app is going to send a message to the message queue, many messages of various events that happen. They're going to stack up in the queue. The worker or workers are going to pull a message off the queue, process it, and then they're going to store the results in, say, the database or a file system or HDFS, S3, whatever it is that they're doing. And that works really, really well until you get to the point where your message queue becomes the bottleneck. So, yeah, I know. It's amazing how that happens, right? There's a bottleneck everywhere you turn around. So what we did to solve this is we wrote a distributed message queue. And this is kind of how it works. The worker still writes its results. The web app still writes event messages to a queue, often running locally within the microservice that we're working with. But, and this is the key part, the worker is listening to a queue that's running on an entirely other server, which allows us to do fun things like that. And that is how NSQ works. But how does the worker find the queue with the topic which it's supposed to be interested in, right? It finds it via sort of a registry service we wrote called NSQLookupD. Notice right here down at the bottom, lookupd HTTP addresses, get the setting for it. There's 2, 3, 4, however many you want, NSQLookupD instances running in your data center. And the way that works is, how do I find things? The first time an app writes to a particular topic, the NSQ writer portion writes to the queue and says, hey, I'm writing to this particular topic, say spam API. At that point, the queue then pushes that topic up to NSQLookupD, which means that when a random worker in an entirely different microservice comes along and says, hey, where can I find the spam API topic? NSQLookupD says, yeah, find it right there. At which point, the worker connects to it and registers a channel. So we have topics and we have channels. Why do we have that? Well, for one thing, it allows horizontal scaling because the way we set up channels, all messages in the spam API topic go to every channel. In this case, we're looking at the spam counter channel. Every time a new worker connects to the spam API and says, hey, I'm looking at channel spam counter, it divides the number of messages by the number of workers automatically. So each worker here gets 1/3 of the messages, and that's all. This makes scaling out really, really easily. All you have to do is spin up a new worker and say, go to town, and it does. Now, the other fun part, every different channel gets a full copy of all the messages coming in on the topic, which means that you can have this spam counter channel here chewing away and incrementing stats D and driving up all of our monitoring numbers on spam because, oh boy, do we get a lot of spam. At the same time, you can have another utility, such as our NSQToFile utility, which logs everything and writes it to S3, which is incidentally how we maintain our canonical backstore of everything that happens at Bitly. Makes life so much easier. Everything gets written to S3. So that's these settings. The settings topic that you get, in this case, NSQD output topic, the channel, QReader spam metrics, and where to find them all. NSQ is open source. Feel free to have a party. It is not Python. It is written in Go, but it is part of the secret sauce, and it's not particularly secret. So we have a number of other users besides ourselves, and we invite contributions and folks who need it. How do we handle this, though? Well, monitoring. This is our less than ideal monitoring setup, but it's far from our real monitoring setup, I guess. But this is a picture of the iMacs that we have stacked in the back of the room. The one on your left there is showing graphite stats, and the one on the right is showing Nagios alerts for our two different data centers. And that's key. We monitor, 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 monitor. If you do not monitor your microservices, you don't know that they're down. They are down, I guarantee you. You just don't know it. Which is one of the reasons that we implement things as simple as panhandler. Panhandler, I didn't bother to show you the code because all it does is def get return OK. If it returns OK, if it returns a 200 OK, then that means that that tornado instance is up and running. That's all we really care about. Or maybe it's not. Maybe it should be some sort of extensive health check which does a deep dive through the database layer, makes sure that the cache exists and is caching everything properly. That's also an option. We have some of those too. Which is great for monitoring. How do you manage NSQ? NSQ comes with a lovely, I want to say it's in Python. I'm pretty sure it's in Python. Obviously, I haven't dealt with that particular bit of code myself. But NSQ admin, which shows you all of your topics. And this is really just the first chunk of a rather long list that I had to cut off to make it at all. Is that readable at all? It's not bad. I'll have to make that better next time. Yeah, so this is broken up per data center. And if we drill down into one of these, let's take the one at the bottom, which is history, which is a history of changes to encoded links. If we drill down into that, we can see all of the consumers of this particular topic by their server name. So this, sorry, utter reverse. These are where all of the NSQDs that are running the history topic are located. There we go. So this is a list of hosts, and you can see that they're processing a lot of messages, but they're not necessarily very high rate. There's a fair number of channels consuming them, which means they're duplicating all of their messages like 8 times each. But because there's not that many coming through at the moment, you don't see any backed up in memory or written to disk, which is kind of a good thing. That means as they come in, they get processed and they go right on out the door. If we drill down into one of those hosts, then we can see in really tiny script here all of the individual consumers and the statistics that they're working through. The other nice part is, and yeah, definitely going to have to improve that. These up at the top are, for instance, garbage collection counters, memory heap statistics, I/O statistics, network statistics on that particular host, which makes monitoring this really, really easy. So to tie things back together, all of our microservices are talking to each other through NSQ in a fashion that looks kind of like, yeah, I had to have one flashy animation. It was, you know, it was fun. Ta-da! So again, yeah, we're not Twitter, we're not Google, we're not Facebook, but we are handling a fair amount of traffic. That's about 3,000 requests a second. We have, I don't know, 300-400 servers that we're managing and running, and we're dealing with, like I say, a fair amount of traffic. So at this point, before I go into specific questions, and as a note, I'm a little hard of hearing, so if I have trouble, I'll just ask you to come by afterwards. But immediately after this talk, we're supposed to have lightning talks at 6 p.m. And again, a huge thank you to our PyGotham organizers for all of their hard work. Thank you, y'all. No, I'm looking at y'all. Thank you. After the lightning talks, the unnamed social event will be held at Bitly HQ and is co-sponsored by Bitly, Continuum Analytics, and Untapped. So I will be hanging around, and then we'll be leading whoever wants to follow me to the NR and Q and then down. Basically, it's Union Square between 16th and 17th, 15th and 16th. Yeah, 85 Fifth Avenue is where that's located. Also, my colleague Sean O'Connor is going to be going in depth into how we handle failure, which makes, you know, life real easy. He's probably a better speaker than I am, so do feel free to come by and see how he handles things. Does anybody have any questions? Jeremiah. Historically speaking, I think at the time that, which was a couple years ago, RabbitMQ was evaluated, but I think the lack of Erlang knowledge in-house combined with them running into instances where Rabbit locked itself hard, and I see some heads nodding. That is a thing that happens. It's an avoidable thing if you know what you're doing. I don't think we knew what we were doing. And we had have a few mad scientists in-house who like to write things. So there's a certain amount of not invented here going on there as well. There's also, so historical reasons, basically. Yeah, the standard for a lot of cases. Anything else? Yes?
How long have you been using this method of microservices? Has it gone well for a year?
Oh, we've been doing it this way for 4 or 5 years, well before the buzzword came out. Yes, this has just been the way we've been working. And hey, Tinder, yeah, it's worked out pretty well for us. Mm-hmm. Not necessarily. We have some cases where our expected load is low enough that we're running a number of microservices all on one server. We have a number of cases where the service in question is doing enough chewy work that we're spreading it out over 3, 4, or 5 servers, yes. But that's key. It gives us the flexibility to do what we need to with it. Okay. Yeah, no, the graph, the directed graph was basically me swinging the BS stick. That said, it's actually conceptually fairly reasonable to look at that as how NSQ is set up. V3 API is going to be sitting in front and proxying requests to all of the various microservices. You're probably right in saying that when you hit a given analytics page or report page of some sort, you're probably hitting somewhere between 2 and 10. That feels about right to me from what I've seen. The thing to realize is that some of those have probably, in the course of their work, either communicated via NSQ or HTTP API or both to some of the other services to collate the stuff that they're doing. So, yeah, it's complicated.
Seems like one of the downsides to having all the services everywhere is that you need to do a lot of serialization and deserialization of all the objects.
We spend a metric crap ton of time doing JSON serialization calls, yes.
Have you thought of using any other protocols to do something like that?
We thought about it and decided to go ahead and suck up the serialization costs simply because having a text-based, simple, mostly human-readable format makes debugging really, really easy.
Okay.
Yeah.
And is there a particular reason that you throw the HTTP status code inside that JSON object instead of just drawing on a header?
Because the header is going to be the proxy header, right? Not just from Nginx, but from v3.
Oh, okay.
Yeah. What we're doing there is we're communicating the status code of the backend service through the status code that gets pushed forward. Yes?
I was just wondering if you could maybe speak a little bit about, like, sort of, you already spoke about sort of like NSQ, the discovery.
Yeah.
Sort of new queues.
Mm-hmm.
If you could just speak a little bit about, like, the service, just service registration and discovery as far as, like, in general. Because if that's like a topic for a whole different talk. But.
It is definitely the tip of a medium-sized iceberg, but the short version is that Bitly grew up before things like Puppet and Chef existed. We do our config management in a. I'm getting there.
Okay.
Yeah, no, we looked at things like Zookeeper and said, oh, there's another point of failure and stuff we don't want to bother with. What we wind up doing is we have a map in our repository of roles to services and then roles to servers. And that's basically our method of making sure that stuff gets from one place to the other in a reasonable way. Yes.
So when you're developing one of these microservices, and it's supposed to talk to 2 to 10 other ones for its data, do you also have those running locally on the same box, or do you have staging environments for each one, or do they just talk to production? I guess, how do you handle developing one of these microservices?
Well, our dev VM runs basically all the services. Staging actually is our API and web layer and talks to production data, which should kind of scare people a little bit, but it means that we treat staging really, really delicately. And I think that's pretty much all I have time for. Again, lightning talks immediately following. And after that, I'm going to be leading a herd of people to NQR down to Union Square to Bitly HQ for Le Party.